So the title that I have provided was Nano-Optics with Phonon Polaritons in 2D materials. That sounds rather general, and actually want to focus a little bit on a specific topic on which we got recently quite fascinated about, namely to explore polaritons in 2D materials to get a strong coupling between molecular vibrations and infrared photons. And actually on this picture here, you see already more or less a complete summary of the talk. So essentially, I will talk about phonon polaritons. I will explain in a second what these are. So essentially, these are electromagnetic waves. They propagate along the 2D material. Here we focus on hexagonal boron nitride. And we excite them with a metal tip of an atomic force microscope, which actually is part of the microscope that Peter mentioned before. This tip is illuminated with the infrared light. It excites these surface waves. They propagate along the 2D material. And I will show you how we can excite them, how we can image these waves. And then in particularly, I will talk about how we can exploit these highly confined electromagnetic waves to get a strong coupling with molecular vibrational excitations. So that's in brief the talk outline I want to talk about. And so now, okay. And that's a brief outline. So in the first part, I want to introduce a little bit polaritons in 2D materials, how we can image them by a technique called scattering type scanning with optical microscopy. That's the technique that is commercialized by the company Neaspect that was mentioned before. And in the second part, I want to really specifically talk about strong coupling between these phonon polaritons and molecular vibrations. So before I start, I want to briefly highlight the people that are doing this work. So the work that is covered today are particularly done by Andre Bilinkin, Marta Autore, Irene Dolado, Panning Li. In the meantime, he's back to China, so was a postdoc for a while, and Diva Vermiane. And the collaborators are the important ones are here: Alexei Nikitin, Pablo Alonso Gonzalez, and Javier Aizpurua. All of them here in San Sebastian. Yeah, here you can see our institute. It may be not so known. It's a research institute of about 100 researchers located here in San Sebastian. And I'm always looking for postdocs and PhD students if I'm allowed to make this advertisement here. So if you're interested, please contact me. So I want to start very basically because I understood that this may be a broader audience here. I want to start with what is a surface plasmon polariton. That's a concept that is rather important in optics and particularly nano optics and has nothing to do so far with the 2D materials. So a surface plasmon polariton is an electromagnetic probe wave that propagates along the interface between a metal and a dielectric. Important is here that we have on the one side a permittivity, oh that's a mistake here, that is smaller than 0 and a dielectric where the permittivity is larger than 0. So these are guided modes, and these modes, they propagate along the interface and they are confined in vertical directions, so they are waveguide modes. And so the fields extend exponentially into the dielectric as well as into the metal. And if we look at the dispersion here, the frequency versus momentum, then we see that the momenta is always to the right of the light line. That means these waves propagate with the wavelengths that are smaller than the photon wavelengths, and for that reason we can shrink the wavelengths of light, and that makes it very interesting for applications where we want to go beyond the diffraction limit of conventional photons. And so this is very, very classic, but now with the emergence of graphene, these plasmonic concepts were transferred to the materials. And here graphene is an extreme example. It's a monolayer, it's a conductivity sheet. If it is doped, we have a negative permittivity, and we can excite in these single monolayers of graphene these polaritons, plasmon polaritons, so that it's important that the graphene is doped. And these waves have an extreme confinement, meaning that they have an extremely short wavelengths and extend perpendicular to the graphene sheet here. If you compare that here to the photon that is shown here, schematically it's only half the polariton wavelengths, the photon wavelengths. So that means by coupling light to a graphene sheet, we can have extreme compression of light. So we can have, for example, infrared photon energies, but wavelengths that will correspond to UV. And that, of course, makes it extremely interesting for generating strong light-matter interaction, for biosensing, for photocurrent detections, nonlinear optics. A lot has been done already. I don't want to talk about that. Just want to point out this possibility of shrinking light is something that attracts an enormous amount of interest because of potential applications in the future. So the problem now is how to excite and visualize these waves. As I said, they are deep sub-wavelength scale, and with a normal light microscope, we could not see or image these waves. But this is what we want to do. And this is where we use a near-field microscopy technique that was originally well, intended to perform chemical imaging, but it turned out that it's also a highly interesting tool for mapping these exotic electromagnetic waves. So I briefly outline it here. So the microscope is basically an atomic force microscope where we use a metallized tip. Then we shine light onto the tip. The tip acts as an antenna. It converts these propagating modes that arrive at the tip into highly concentrated near fields at the very tip apex. Here we see a numerical simulation of the field enhancement and distribution around the tip apex here, which is typically 20 nanometer. So we get a extremely confined spot. We bring that close to the sample surface, and now these near fields contain high enough momenta to eventually launch these plasma polaritons in the graphene sheet. So that's the excitation process. Now these modes propagate away from the tip, and eventually they hit an edge. They cannot exist outside graphene, so what happens is they are back reflected, and a standing wave pattern is formed between the tip and the edge here. And now the tip, by scanning the tip here and recording the scattered light, we get images such as the ones that you see to the right, where we see here graphene that was epitaxially grown on silicon carbide. And this image now is rather homogeneous on the silicon carbide, because here we see material contrast, but inside the graphene, you see here these fringes parallel to the edge here. And these are the interferences that are created through the propagation of these polaritons on the graphene sheet here. So the fringe spacing is here lambda over 2, the polariton wavelengths over 2, and in this case, we illuminated the tip to 10 micrometer, and we observe here a polariton wavelengths of 230 nanometer, which is a shrinking of the wavelengths of light by a factor of 40. So that's an extreme confinement, and that makes things extremely interesting. However, there are not only graphene plasmons, there are many more polaritons in 2D materials, and I show here a figure from Dimitri Basov's science review paper, which I like very much because it summarizes all that is going on here. So it shows again the 2D material in this case, where we require a negative permittivity in the 2D material embedded in a dielectric environment. Now, if light couples to electrons in doped graphene, then we talk about plasmon polaritons. So I talked about them. But what we can also have is we can have optical phonons and insulators, such as, for example, hexagonal boron nitride. I will show this in a second. We can have negative permittivity too. And then we talk about phonon polaritons. That's the topic of my talk. But there are other excitations that could give rise to negative permittivities. If we have strong excitons in semiconducting materials, then we could excite exciton polaritons, and actually they have been observed already in various 2D materials with this near-field technique that I described above. Then what has not been observed yet, but theoretically predicted, are Cooper pair polaritons, Magnum polaritons, and so on. So there's a lot to be explored. So these polaritons in 2D materials are particularly interesting because, first of all, because of their thinness, we get an extreme polariton confinement, meaning we can shrink light to extreme dimensions. Then in graphene, we can tune carrier density. We can have active control of the polariton wavelengths. What is also very important, these excitations here have typically very low losses, and that means we have long polariton lifetimes. We have an anisotropic crystal structure which gives rise to very exotic propagation of light, but I don't want to talk about this here in this talk. So let's come to a hexagonal boron nitride and its optical properties. Here show the permittivity in the mid-infrared spectral range. And we have here two so-called rest bands. I want to focus on the upper one. So here between about 1350 and 1600 wave numbers, the in-plane permittivity of boron nitride is negative. The out-of-plane permittivity is positive, but it's enough that one of the permittivity components is negative. This gives rise to polaritons that propagate now along here these exfoliated HBN flakes. So typically work with a hexagon with exfoliated flakes in the range between a few nanometer and several tens of nanometer. So the first one actually who saw these Phonon polaritons in hexagonal boron nitride was Dimitri Basov's group. They used exactly the same technique as I showed before for graphene. The only difference now is that we excite phonon polaritons rather than plasmon polaritons. In the following, we will describe these polaritons quite often in these typical dispersion diagrams where we plot the frequency versus momentum. And here we see the calculated dispersion for hexagonal boron nitride. That's plot that I show here covers more or less the threshold band where these polaritons exist. And we see here that this dispersion is always to the right of the light cone here. So we see here that the momenta can be dramatically increased compared to that of the photon, meaning that we have extremely short polariton wavelengths. So before I go on the topic of strong coupling, I want to give you some examples of what one could potentially do with these waves without going into detail. I just want to give you a little bit of flavor, what is possible. These are all things that we did over the last years. So as I said, the wavelengths is extremely short, and I talked so far about slabs, but one could also think of making small ribbons out of HBN that then could act as waveguides for these polaritons, extremely small wavelengths. Here, for example, we have a ribbon that has only a few hundred nanometer widths, and we can see here these wave patterns along this ribbon here. These are phonon polaritons at 1440 wave numbers. So that is a wavelength of about 5 to 6 micrometer. But the wavelengths here in this ribbon that we can guide with this ribbon is in the range of hundreds of nanometers. So this could be extremely tiny infrared waveguides just by coupling infrared light to phonon polaritons in these ribbons here. Then one can also make meta surfaces out of that. In this case here, we made a grading structure into the HBN by lithography and reactive ion etching. And in this case, we have a grading structure. We have ribbon widths of 100 nanometer, and they're separated by a very small gap. And in principle, we can consider this as tiny little waveguides, such as the ones shown to the left here. But now they are so close that wavelength coupling occurs. And in this case, this surface acts as a meta surface, and exotic wave propagation occurs that we can see here to the right. I show here a topography image where we see the pristine HBN, then the grading structure. And on top, we placed a metal antenna. And this metal antenna now acts as a light concentrating device, and it creates a bright near field here at the edge here, which launches then polaritons that propagate along this grading here. And in the schematics here, or in this topography image, I indicated the wavefronts with which these polaritons propagate. So normally they would propagate with a convex wavefronts here, radially out propagating waves. But through this waveguide coupling in these HBN ribbons, we create here anomalous wavefronts. We see here that the wavefronts are actually concave. They are the opposite as what one would expect here. And that is what is called an in-plane hyperbolic meta surface. As I said, I don't want to go into detail here. Just want to say we can play interesting games with these HBNs and phonon polaritons in a very similar fashion than what people are doing typically with thin metal layers. And in the near field microscope, we can observe these anomalous wavefronts here. We can also make resonator structures, and that brings us already closer now to the topic here. We can make resonators by just cutting these waveguides here into small pieces, and then the polaritons that are excited here in this waveguide with the help of the laser illuminated metal tip, they cannot escape. Once they are excited, they propagate forth and back into these truncated waveguides here, and they perform Fabry-Perot resonances here. And here we can see several modes. So we image always at the same wavelengths here. And we can see here for the short cavity here, a resonator, we see here a bright spot here at the edge here to the right here. And then in the center, this corresponds to second order dipolar mode. It's actually a kind of a dark mode that would not be excited by far field illumination just because of symmetry. But with the help of the tip, we can clearly excite this mode here. Then if you make the waveguide longer, we get the next order mode and so on. So we see here beautifully all these modes. And one could say in principle, these HPN truncated waveguides, they have the same function as a cavity, just instead of infrared photons, we have infrared phonon polaritons. And for that reason, we can extremely shrink these resonator structures. And that makes it highly interesting if you're interested in sensing, for example. And that is one of the ideas we had. We wanted to make ribbons in which phonon polaritons resonate. And because of their short wavelengths, the field extends very little outside. And so the idea would be, if you now place molecules in the vicinity of these ribbons, they would be illuminated by these strongly confined and enhanced fields provided by these hexagonal boron nitride phonon polariton resonators. And this idea is nothing that we invented. This is an idea that comes from a technique that is called surface enhanced infrared absorption spectroscopy, in short SIRA, that is typically done with metal resonators in the infrared. So the idea is to enhance vibrational spectroscopy by exploiting these resonances here. And this is what I want to talk about here. That's just here a brief outline. So we created these ribbon arrays. We put molecules on top. We performed spectroscopy, and we saw features that resembled us not only to enhanced vibrational sensing, but also to strong coupling. And so we got into this topic of strong coupling and got fascinated by that. And that's what I want to talk in the second part of my talk. And so far, I introduced a little bit what is a phonon polariton, how can we excite and image them with the help of near-field microscopy. Now I want to talk about strong coupling and want to give a brief introduction to strong coupling, briefly mention what we mean by that and why this is interesting. So strong coupling in photonics plays an important role, and there are various implementations of strong coupling. One of the typical experiments would be that one places molecules that have some dipolar excitations, excitons, vibrations, and so on, into a classical microcavity. And if one manages to match the molecular resonance with the cavity resonance here, and in case the initial states exchange energy coherently faster than the decay rate, then new eigenmodes appear, hybrid modes appear, and we get bonding anti-bonding modes if we have exactly the matching between the molecular resonance and the cavity resonance. This is strong coupling. As said, there are many implementations of that, and strong coupling in manifest. If you look in a dispersion diagram, here we plot energy versus momentum. We have the excitation at a fixed frequency, and then we tune the cavity length, for example. We get the dispersion of the cavity would be this tilted line here. So these dispersions, once we achieve strong coupling into this cavity, these two dispersions wouldn't cross, they would anti-cross, giving rise to a mode splitting here. This mode splitting that is in quantum optics known as Rabi splitting. I don't want to here talk about Rabi splitting, but because what I will talk here about is classical strong coupling, has nothing to do with quantum effects. I want to point this out because it often leads to confusion. So this is normal mode splitting here by the energy here we denote by omega. So why is this interesting in the infrared and with molecular vibrations? Well, there were a bunch of papers recently, essentially by Thomas Ebbeson's group. So they showed that by placing here into this cavity molecules and make this cavity such that the molecular vibrations resonate with the infrared cavity resonance here, then several interesting effects could happen. So the physical and chemical properties of this material could be changed due to the strong coupling. So reaction speeds could be modified, that was reported, or conductivity could be changed. And so that's why this is a highly interesting topic, but typically this vibrational strong coupling is performed with a large amount of materials in these microcavities. So these microcavities have typically micrometer size dimensions, and one has a large amount of material. And so we were wondering whether strong coupling could be achieved with a much smaller amount of molecules by exploiting these highly compressed field provided by Phonon Polariton resonators. So of course, the vision would be to achieve vibrational strong coupling with individual molecules. I should say we are far away from that. One could expect interesting quantum effects. But the first step towards this vibrational strong coupling with a really extremely small amount of molecules is to really demonstrate that we can go beyond classical microcavities and can couple eventually with a few nanometers of layers. And that's what we did. We made ribbons out of HBN, again by etching, and we tuned them such that the width here matches half the Phonon Polariton wavelengths. And then we did, in this case here, a far-field experiment. And we tuned this ribbon width here. We see that in the transmission spectrum, we see here a dip. This dip corresponds to the resonance, the fundamental resonance of these ribbons. Then we increase the ribbon width, and we see that the dip here in the spectrum shifts to lower frequencies. This is exactly what one would expect for classical resonators. It's simply because the polariton wavelengths becomes longer with smaller frequencies here. So now we placed molecules on top of these ribbons here, in this case 30 nanometer, only a really thin layer of molecules. The ribbon width is in the range of 200 nanometer. And it's the same ribbon array actually, and we see once these resonance of the ribbons moves to lower frequencies, we see that it does not really cross. We see here kind of a clear anti-crossing feature. And once the molecular resonance and the resonator match, we see this double peak structure. I think I forgot to mention that here the molecule that we put on top is CVP, that's organic semiconducting molecule. And here we see the spectrum of a thin layer just on a calcium fluoride, and we see here this molecular resonance as a very faint feature here. So it's barely visible. Also, this was a 100 nanometer film. So once we put this a 30 nanometer film on top of these ribbons, we can see that this molecular feature is really strongly enhanced. So that would be, let's say, one could call this enhanced sensing. This would be a classical surface enhanced infrared absorption spectroscopy phenomena. But once we saw this, we thought, well, this kind of splitting of the resonator peak could indicate already strong coupling. And so we analyzed this in a little bit more detail. And we followed here the standard approach that is done in many of the strong coupling experiments. So we assume that we can describe the molecules by one harmonic oscillator and the ribbons by one harmonic oscillator. They are coupled via a coupling strength G. And so we developed this or used the standard equations for a coupled harmonic oscillator. And we do the following. We keep the damping and energy of the molecules fixed because there's that we know from literature. And as a fitting parameter, we choose the coupling strength G, the damping, and the energy or the frequency of this Phonon Polariton resonators as fitting parameters. And as you can see here, the red lines here, they extremely nicely fit the black curves here, which are the experimental spectra. And from this fitting, we can actually extract the eigenmodes, the eigenmode frequencies. I want to point out here that it's not the dip splitting here that gives us information about the peaks. Very often it's the case, but if we are close to the strong coupling limit, we really need to derive the eigenmodes, not the dips. The eigenmodes could be different to the dip positions here. And so that's what we're doing here. From the fitting, we get all these parameters, and then we can take the equation for the normal modes and calculate the energies of the new hybridized modes that occur due to the coupling of these molecular vibrations and the resonator. And this is what we get here. We plot here the hybrid mode frequencies versus the frequency of the original Phonon Polariton resonator. And these are now the eigenmodes. These are not dip positions. These are eigenmodes. And we can see here a clear splitting of this eigenmodes here. We get splitting of about 12 wave numbers. And we can analyze this. Don't want to go here into this mathematics, but one can show that these 12 wave numbers really correspond to strong coupling. That means in the situation that we have here, if we think about the original oscillators, namely the molecule and the resonator, they exchange energy faster than they decay. And for that reason, two new eigenmodes occur. So this is now a polariton, kind of a polariton that is formed by a molecular vibration and a phonon polariton. And this strong coupling is here achieved with a really small amount of materials and resonator structure compared to a microcavity. So we were now wondering, well, can we actually see this coupling also in the near field? Can we spatially resolve this coupling between molecules and the resonator? And therefore, we did not only far field spectroscopy, but also near field spectroscopy of these ribbons. So first, we did an experiment where we look at these ribbons without any molecules, because we wanted to see what mode do we excite in these resonators. In the far field, we get here the dip, we see there's a resonance, but without any calculations, we cannot really say, is that a dipolar mode or is it second order mode? So that's why we image with the tip across the ribbon, and we take at each of the pixels an infrared spectrum of the light that is scattered by the tip. In this case, we get this plot here where we have the frequency on the horizontal axis, and on the vertical axis, we have distance from here to here. And what we see here, if we go along this direction horizontal, we see here a resonance peak, and this resonance peak here is located here at the edge of this ribbon. And we see another bright spot here on the other side of the edge here. So if we read this diagram in horizontal direction, we see the spectral peak position. If we read it in this direction, then we get the mode profile without any calculation. And we see that there's a lot of field concentration at the two edges of this ribbon here, which tells us without any further calculations that this is the fundamental dipolar mode that we excited here. So now we repeated this experiment, but we first evaporated the molecules. For comparison, the far field experiments shows us here that this resonance is splitted. We see two dips here. And we now repeat the experiment with the tip. We scan the tip across. We recorded each pixel a spectrum. And what we see is, again, we see that, first of all, we see a splitting in the near field too. And we see that these bright spots here, they occur at the edges of the ribbon here. So again, we see that we are still exciting the dipolar mode. But this dipolar mode now is, as in the far field, exhibits this kind of splitting of the mode, which indicates strong coupling. But this is now really visualized. Now we can trace a strong coupling with, let's say, at each of the individual pixels along the ribbon. So that's a far field experiment measuring the complete response. And this is a local probing of strong coupling. And we were quite fascinated on this, but we soon realized that actually there are a couple of strange things going on here. And it turned out that the tip is acting as here an antenna concentrating the light field, eventually may influence this strong coupling, and may actually need to be considered as a third oscillator in the game of coupling between molecules and ribbons here. And actually at that time when we did these experiments, a paper appeared by Marcus Raschke group who did similar experiments, but with metal antennas. And in their paper, they described that indeed one needs to consider this metal tip here as a third oscillator that eventually may enhance the strong coupling between the molecules and these resonators here. So this is something that is still not elaborated. This is work in progress. It's not published. So we think this is quite fascinating to measure or visualize strong coupling in the near field, really locally resolved, but there are a couple of issues to be solved. And for that reason, we came up with another idea how one could study with a near field microscope strong coupling. And we performed here polariton interferometry, the technique that I showed you before without any resonators. And the idea is illustrated here on the left side. So we take an unstructured hexagonal boron nitride flake and we put it on top of molecules. We don't structure anything, and we scan the tip on the opposite side. So that way we avoid the coupling between the tip with the molecules, but we can efficiently excite the phonon polaritons in the HBN layer. The idea is now that the phonon polaritons, they propagate as before to the edge of the HBN, they are back reflected, and we trace that. But on the way, forth and back to the edge here, the field penetrates into the molecules. And that way, this polariton may couple with these molecules, not in a resonator structure, but in this kind of propagating fashion. And this we can see nicely here in a numerical simulation, where we mimic the tip by a point dipole source, here this bright spot, and we scan this bright spot perpendicular to the HBN edge. The tip here, or the dipole, excites this mode. We can see this mode propagates to the edge and is back reflected. The standing wave pattern is formed, as you can see here in the field distribution. But more importantly, we see that indeed this polaritonic field and the polariton interference involves heavily this layer here, this molecular layer that is just below the HBN. So it shows already, well, this with this method, also the tip is on the opposite side, we can nicely create a coupling between the polaritons and the molecules that are below. And hopefully the tip is not coupling directly with the molecules. So we did then the following experiment. We take a broadband infrared source, we illuminate the tip, and we collect the tip scattered light. Now we have a broadband source. We need to do spectroscopy, and the spectroscopy is accomplished with a Fourier transform spectroscopy module here. So we call this technique nano-FTIR. It is an FTIR technique, and just instead of measuring transmitted light, we do spectroscopy of the light that is scattered from this AFM tip here. So first we start scanning HBN on a substrate without any molecules, and we get plots that are shown here below. We measure at each pixel as a function of distance between the edge and the tip here. We measure spectrum. The spectrum is shown in vertical direction. And we can see here these fringes, this fringe pattern here, with a fringe spacing that changes clearly with frequency. So if you had a fixed frequency here, we see clearly this polariton oscillation. This fringe spacing here is half the polariton wavelengths, as I explained before. If you go to higher frequencies, we see that the fringe spacing and thus the polariton wavelengths decreases. This is just because the frequency increases here, and the momentum of this polariton becomes larger, as I explained before. Now, in order to get the experimental dispersion out of these measurements here, it's rather simple. We just perform a Fourier transform along the horizontal direction here, and we immediately get the dispersion here. And the dispersion is shown here. Interestingly, we see here two branches. This may be a little bit surprising at first glance, but I can tell you that what we see here is the dispersion of one and the same polariton mode. The difference is here that this branch labeled T corresponds to the polariton that is launched by the tip, propagates to the edge, and then is back reflected. So this polariton propagates twice the distance between tip and edge here. On the other side, due to this global illumination of the scheme, we need to imagine that we have a diffraction limited spot that has tens of micrometer of diameter. This illumination spot also illuminates the edge of the HBN. And this edge allows one to couple polaritons into the HBN, similar to what the tip is doing. This polariton propagates to the tip and then is scattered out. So this polariton propagates only the distance between tip and edge here once. And that is here the E branch. As I said, it's one and the same polariton. The E branch here would give you the polariton dispersion, while the T branch gives you the polariton dispersion multiplied with a factor of 2 if you consider the momentum axis here. So now we repeated this experiment, but we put the molecules below, and we see a dramatic change of this measurements here. We see that these interference fringes are interrupted. We see they are slightly bended. And in Fourier transform, we actually see strong interruptions and bending of the dispersion itself. This indicates already that there's a strong interaction happening between these propagating modes and the phonoparitons in the HBN. So On the other side, with this technique, we see that the signal to noise is not very good, and we had a little bit of problems in analyzing this. So we performed a zoom in into this region here. We now focus on the branch of the tip launched and tip detected polaritons. And we used single wavelengths imaging in the spectral range around the molecular resonance. So we took images with a powerful laser so that we get a good signal to noise ratio and with a high spectral and spatial resolution. We get these images and the line profiles you see here, and they are taken in very narrow spectral distances here. These are line profiles, and we see that with increasing frequency, the polariton wavelengths decreases, but then suddenly around the molecular resonance, we see that the wavelengths actually starts to increase before it decreases again. And this is a classical observation of anomalous dispersion that we know from standard optics. But now we see this anomalous dispersion induced by the coupling of molecular vibrations with these Phonon polaritons. Now we do the same as on the slide before. We Fourier transform these line profiles to assemble a plot in the same fashion as we did before. We have on this vertical axis, we have the frequency and the momentum. And here we plot the Fourier transform. Each line profile corresponds here to one line of Fourier transform. And this is now our polariton dispersion. It's a little bit difficult to see things here because of the pixelation here, but we can analyze this Fourier transform. And the first thing we did is we extracted line profiles in the horizontal direction and determine the maximum here. And that way we trace the polariton dispersion. We see here, that's the polariton dispersion increasing. That's what we would expect for hexagonal boron nitride phonon polaritons. But once we cross the molecular vibration here at 1450 wave numbers, we see this backbending, so-called backbending here. We see the momentum decreases, which corresponds actually to the increase of the wavelengths. So this anomalous dispersion here induced due to the coupling between the molecules and the phonon polariton. This negative slope here corresponds to a negative group velocity actually. This is not a big deal. So a pulse would propagate backward, which does not mean that the energy propagates backward. That is just a reshaping of the pulse shape due to this negative group velocity induced to these molecules. On the other side, we can analyze this data by extracting line profiles in the vertical direction at a fixed momentum. And this actually would correspond to an experiment that we would make with ribbons of a given width. So we fix here the momentum. And if we analyze that, then we see that instead of a single peak here, we get two peaks here, which reminds us very much to the far-field experiment that we did before. Now we can take again the harmonic oscillator in the same fashion as I described above and fit these line profiles to determine the eigenmodes of this hybrid mode that we obviously observe here. And if you do so, then we get the data points that are here drawn in black. So these are the eigenmodes that we derive from analysis in vertical direction. And we again see here a splitting of the dispersion here. This omega again corresponds to 11 wave numbers. And the phenomena that we observe here is the same as in the far-field experiment. The difference is here, we did not structure the HBN, but we performed polariton interferometry. And this way we can extract strong coupling phenomena and features in the same fashion as we do with far-field spectroscopy, but we don't need to structure it. So we compared that with the theory, and to that end we performed transfer matrix calculations. We calculated the imaginary part of the reflection coefficient of this stack of HBN molecules and the substrate. And we plot the imaginary part, which is this color plot here in the background. And you see already it resembles very strongly to the experimental data. It's just more cleaner because we have here more frequency and momentum resolution. And now we can do exactly the same. We can analyze or extract dispersion and eigenmodes out of these Fresnel reflection coefficients by looking for the poles of these reflection coefficients. And we can do this in two fashions. We can assume that we have a complex valued frequency. And in this case, the poles give us a dispersion that is here indicated by the white lines here. And these white lines here, they correspond very well with the experimental data that we extracted from the plot before. We can analyze this data in a different fashion, namely assuming that we now have complex valued momentum. And in this case, we get dispersion that exhibits here backbending, exactly the same fashion as we obtain with in the experiment. So I want to point out here that what we do here is we analyze one and the same data set, but we assume different phenomena. The complex valued frequency would actually correspond to a far-field experiment of ribbons, while here in this schematics here, it was actually derived by using a CW laser and performing real space imaging. And a CW laser, in principle, it has a real frequency, and the momentum is complex. So it's just a matter of consider or how we interpret the experiment, whether we get here this normal mode splitting or this backbending here. But the phenomena that is the basis of all that is the same, namely the coupling, or strong coupling between the molecules and the Phonon polaritons. And I want to point out here that what we are doing here is nothing really that we invented or that is new. This type of analyzing strong coupling between polaritons and molecules is something that is done since many years in so-called surface plasmon polariton spectroscopy in the Kretschmann configuration. I want to briefly outline. So very often the interaction between surface plasmon polaritons on metals with adjacent molecules is done. The surface plasmon polaritons on metals I introduced on the very first slides of my talk. And these metal surface plasmon polaritons, they don't have that high momenta. And for that reason, they can be excited in this Kretschmann-Ritter configuration, where a laser beam is passed through a prism, and through total internal reflection, these surface polaritons are excited. So tip is in this case not needed. In this case, we have the possibility to change the frequency and this angle here, the illumination angle. And we can map the reflection of of the beam is reflected here at the metal surface. And this reflection patterns that we observe here resemble very strongly what we have seen with a near-field microscope. If we have polariton excitation, then the reflection here strongly goes down because all the energy goes into the polariton. And we see here these dispersions that are created through the absorption of or the light into, or the transfer of light from the incident beam into the polariton. Now we see exactly the same if we take these energy versus momenta plots and we analyze them via line profiles that are vertical. We get here a dispersion that exhibits here anti-crossing feature. And if we make cuts horizontal, we get again the backbending feature here in these plots here. So it's exactly the same that we were doing with a near-field microscope. So I want to point out, while this can be done with the polaritons on gold surface, polaritons where the momentum is enhanced by a small factor compared to the photon wavelengths, this technique cannot be applied to Phonon polaritons in 2D materials, simply because the Phonon polaritons, or generally polaritons in 2D materials, have extremely high momenta, and we need another technique. And this is essentially what we showed here. We can use polariton interferometry with the help of near-field microscopy to study strong coupling features in a similar fashion that one could do with the Kretschmann-Ritter configuration. There's a lot of information and literature already around, and all that can be readily transferred to analyzing data obtained with a near-field microscope. Okay, so let me, I don't know how much time do I have still? should come close.
You're a bit over time, so you should think about rounding off.
Mm-hmm. Okay, so let me just finally give you a brief outlook on what one could do. So I said the motivation for this study was we want to achieve strong coupling between molecular vibrations and infrared light in extremely small dimensions here. And so we performed an experimental study where we calculated dispersions as a function of thickness of the molecules and of the HBN. And let me start here. Let's assume we have a 35 nanometer thick layer of HBN, and we increase the thickness of the molecules here. What we see is that the spec bending region increases, or in other words, the normal mode splitting increases here. So this is classic, as in a microcavity. The more oscillators we have, the stronger the coupling becomes. Now we can calculate actually the mode splitting as a function of the molecular layer thickness. And let me start here with a HBN layer that has 35 nanometer. In this case, we can reduce the thickness of the molecular layer down to 20 nanometer, such that we stay in the strong coupling regime. So we cannot go down to really thin molecular layers. However, if we reduce the thickness of the HBN, then in this case, as you can see here, reduction of the thickness of the HBN reduces the wavelengths of the Phonon Polaritons and the extent of the field to both sides of the slab. And that way we can shrink the mode volume to extreme dimensions. We can shrink it to areas that cover only a few nanometers around the HBN layer. And in this case, if we reduce now the thickness of the HBN to layer thicknesses of about 1 nanometer, we stay all the time in the strong coupling regimes, even if the molecular layer thickness is reduced to about 1 nanometer. So with that, I want to, let's say, predict or propose that one should look at extremely thin layers of 2D materials that exhibit Phonon Polaritons or other type of Polaritons. Bringing them close to monolayers of molecules might be a chance to really achieve strong coupling on really extremely thin layers eventually, and in the future with a very few molecules. This is a regime that, at least with the molecular vibrational coupling, has been not achieved so far. And I think these Polaritons in 2D materials are a promising opportunity to get into this regime of vibrational strong coupling with a few molecules. And I think with that, I'm at the end. I hope I could show you a little bit and explain what Phonon Polaritons are, what their basic features are, how we can image and then with a near-field microscope. And also hope to convince you that these Phonon Polaritons, due to their extreme light concentration and confinement capabilities, are interesting candidates to promote strong coupling with extremely small amount of materials. Yeah, and with that, I'm in the end. I'm looking forward to your questions.